Given infinite time and infinite processing power, are there things computers will never be able to do?
Yes.
The year was 1928. Wilhelm Ackermann and his colleague David Hilbert were mathematicians at the University of Göttingen in Germany, and they had a problem, ein Entscheidungsproblem, a decision problem. The point was to prove whether or not any mathematical statement is either true or false based on a set of basic rules. Hilbert, at the time of posing this question, was optimistic an algorithm could be found to solve this straightforward question. Can every statement be proven whether to be true or false? Around 10 years later, British mathematician Alan Turing introduced the concept of the Turing machine, a machine that is often considered a conceptual precursor to the modern computer. It consisted of a theoretical infinitely long tape divided into an infinite amount of cells, kind of like bytes on a computer, except each cell could hold any number or letter from a finite alphabet. On the Turing machine, there is also a head that can go along the tape like a needle on a record player. The machine's head could read the symbol currently under it, change the symbol, move left or right along the tape, or halt, meaning end the program. There are only two outcomes of a Turing machine program. It could either halt or move endlessly in an infinite loop. With this, Turing made his own version of the decision problem, the halting problem, which asks, is there a general algorithm that can determine, for any given Turing machine input, whether the machine will eventually halt or run forever? Using his theoretical machine, he made this theoretical scenario. Imagine a super smart machine that takes an input in the form of a program, and either returns true if the program ends up halting, or false if it goes in an infinite loop. Let's call this machine S. Now, let's make a new machine. A machine that also takes a program as an input, but it returns the complete opposite of what is given. Let's call it D for different. So, we have two machines. S, that returns whether or not a program will halt or loop, and D, that returns the complete opposite of what is given. The problem stems because D is technically a Turing machine program, so we could use it as an input for S. So what will happen? Well, we know that S should always know if something will halt or loop, but since D flips that answer, if S thinks it will loop, then it will halt, and if S thinks it will halt, then it will loop. This means that S can never truly know if D halts or loops, which proves that there physically can't be a computer that will know everything, and Hilbert's decision problem was put to rest. What else can computers do? Do computers really think that point 1 and point 2 is equal to that? Well, that must be because I coded in Python. Let's put it into a real language like Java.
The numbers, Mason. What do they mean? Where are they brought?
I don't know anything about any numbers.
Why do computers get confused with basic math? To answer this, we first need to understand how computers comprehend numbers. In computers, real numbers are often represented using a format called floating points, which involves converting numbers into binary. As an example, let's convert 0.2 into binary for the computer to read. To convert a decimal into binary, we need to recursively multiply the fraction by 2, and then record the digit to the left of the decimal point. It could either be a 1 or a 0. We will continue this process until the decimal becomes 0. Alright, so this is what we're doing. Imagine this like a table. We're going to start with point 2. Then we're going to multiply it by 2, which gives us a 0.4. The binary character is the number to the left of the decimal point. Then we're going to do the same for 0.4. We're going to do this as long as we can. Alright, do you see the issue yet? As soon as it gets back to point 2, it restarts. So this pattern will go on forever. Similar to how 1/3 in decimal notation is represented as 0.33333333, it can never be shown perfectly. The same issue is encountered in our binary calculation. Since a computer can't accommodate for an infinite amount of binary digits, it resorts to rounding. This rounding process results in binary representation that is close but not exact. This is why computers have trouble doing basic math. Now look at this. When I click this button, I get a number, and even though the code I am using sets the number to a random value, it is not random. It's pseudo-random. Computers are only able to do exactly what you tell them to do. So, if we want random numbers, what we could use is something like a linear congressional generator. First, we need to fill in our constants a, c, and m with any numbers. Let's say a equal to 5, c equal to 16, and m equal to 7. Second, we need to set x, which is our seed that our generator will use to start with. Let's pick 84. What this is doing is basically taking the original seed x and then doing a bunch of random calculations to get a random number. First, we multiply a times x and then add c. Then we do 436 modulus our m, which is 7, and that gives us 2. This is our first random number. Now 2 is our new seed, and all we need to do is feed that 2 into the same equation. And this will forever give us random numbers. 2, 5, 6, 4, 1, 0. This seems random so far. 2, 5, 6, 4, 1, 0. Okay, these numbers are not random. What's going on? This type of fake it till you make it randomness is why we call it pseudo-random. It's a deterministic algorithm. This means all numbers that are generated can be predicted based off the seed. However, if we could find a way to make the seed more random, we can generate more random outputs. There are various ways of doing this. Some programs grab things from your computer, such as your mouse location on screen, the time of day, or network-related events, such as packet arrivals or network latency. It could then plug those numbers into the equation, which is random enough for most programs. A common way of getting random numbers is with noise. It can generate numbers that appear random and are less predictable than those from the simple algorithm that we used. Some go as far as to take things like stars in the night sky as an input. They can measure how intense the light is going through the telescope and use that as the seed. But even with all this, computers can generate truly random numbers. If someone knew what all the constants were, they could technically be able to reverse engineer any number generator. Well, that's the video. I hope you guys found it informative or entertaining. Have a great day.